Welcome everyone to Worksheet 5E. Now let's think about part 2 of synthetic strategies. So we have studied about the chemical reactions of carboxylic acid and their derivatives. And it is time to put together all those pieces and figuring out a multiple synthetic steps. First, predict the major product for each reaction. We have six-member ring structure and the functional group is carboxylic acid. So here, carboxylic acid. For carboxylic acids, please note that this one is acidic. That's the main difference between carboxylic acid and other carbonyl compounds or carboxylic acid derivatives. The pK value is around 4 and 5. It is among organic compounds, it is quite acidic. And here we have thionyl chloride. And this is really good way to activate carboxylic acid into a acid chloride. And this is more reactive. Acid chloride is or acyl chloride is most reactive among all the carbonyl compounds. And why this one is working, carboxylic acid is more stable and acid chloride is more reactive, meaning more unstable. So this is really uphill, going from stable to unstable, uphill in energy wise. This is unfavorable reaction thermodynamically. This is moving toward the product because it is irreversible process, because gas is formed, gas is leaving the solution, leaving the solution irreversibly. And now chloride ion is forming like this way. Okay, so because of this sulfur dioxide gas is forming and leaving the solution, we are activating more stable carboxylic acid into acyl chloride. And then from there, we can do many reactions. This one, many chemical reactions we can perform on this acyl chloride. So there are two effects. First, we are removing the acidic proton. Second, we are activating the carbonyl group into more reactive acyl chloride. Second, we are given a benzene ring and the functional group is carboxylic acid. And we are reacting this one with alcohol. Let's go into the alpha carbon of alcohol. And this is primary alcohol. Primary alcohol in acidic condition. Acid catalyst. Then this is carboxylic acid and alcohol reaction in acidic condition. We call this one Fischer esterification. Fischer esterification. This is one of the condensation reaction. The carboxylic acid and the alcohol reacting, it will be forming the ester here and O 1, 2, 3, and this one. The ester is forming and the OH group is leaving as water. So this is one of the condensation reaction. So please remember the reaction condition. Fischer esterification is one of the important chemical reactions for this chapter. And carboxylic acid and like alcohol together in acidic condition, they are making ester and the byproduct is water. So we need to take water out to make the equilibrium moving toward the product side. And C, we have an amide. Here we have amide right there. Let's write the functional group present in the product is amide. And aqueous acid, here we have aqueous acid. And heat is right there. And this is condition for acidic hydrolysis. The amide is stable. Amide is not reacting, not much. So we need to make a strongly acidic condition. Plus, we need to make the temperature going up. Then we are cleaving cleaving this bond, and it is forming a carboxylic acid. Carboxylic acid from water, and the amine is leaving as protonated, or because it is in acidic condition, it can be forming ammonium ion. Okay, and D, we have bromine alkyl halide right there. So this alkyl halide, let's go into the alpha carbon. So this is secondary alkyl bromide, and we are using magnesium in diethyl ether solvent. So this is excuse me, preparation of Grignard reagent. Grignard reagent and dry ice followed by acidic workup. This is extension of carbon skeleton by one carbon plus making carboxylic acid. We are making this inducing carboxylic acid. So let's make this one and one carbon carboxylic acid. That will be the product. And E, we are functional group. Our functional group is bromine alkyl halide, and the alpha carbon is two alkyl groups. So this is secondary alkyl bromide, and we have nitrile right there. And potassium cyanide. Cyanide ion is relatively strong. Not that strong, but relatively strong nucleophile. And this is also good base. Not that strong base, but good base. And here we have alkyl bromide, and the SN2 reaction will occur. SN2 reaction, and it will be forming excuse me, dinitrile. And here, because it's SN2, it is flipped. So up position is changed into down position, like this way. And this condition is acidic hydrolysis. Water and acidic condition and heat. So then the nitrile will be first converted into an amide. Amide is now finally converted to carboxylic acid. So here, this one is carboxylic acid. Again, this is carboxylic acid, but their relative regiochemistry. Okay, so flip SN2 reaction is a flip of up position changing to down position because it's backside attack, and followed by acidic hydrolysis, not turning nitrile into carboxylic acid. And E, we have ester right there. Here we have an ester. And sodium hydroxide in water. So this is biphasic reaction in heat. So this condition is basic hydrolysis. So the sodium hydroxide will be attacking, hydroxide ion will be attacking the carbonyl carbon push up, and it will be regenerated and oxygen is leaving, oxide ion. So we'll have this oxide ion has left, and plus carboxylate ion. OH. First, let me draw this one. After nucleophilic attack, it becoming carboxylate ion, acetic acid, and this one is deprotonated. This one deprotonated right there. So then it will be forming carboxylate ion. It's making the reaction very favorable. This one, and after acidic workup, then oxide ion will become alcohol, and Carboxylated ion will become carboxylic acid. Now let's move up to this one. We have four-member ring structure and methyl group, and this ester group is in down position. So then the only functional group is this ester. Ester. And CH3CH2 MgBr. First, this ethyl magnesium bromide, first equivalent. So then this CH3, CH2, this carbon ion will attack the carbonyl carbon push up, and later the lone pair coming down, regenerating the double bond, and oxide ion is leaving. So it is now here oxide and ethyl group and O methyl, and oxide ion is coming regenerated and methoxide is leaving, so it is generating methyl group and ketone plus methoxide is left. This one, and this is ketone. Ketone is more reactive than the ester ketone. So second equivalent of this carbon ion will attack more readily upon this ketone, and it will be forming, and tetrahedral intermediate. We have methoxide, methoxide, and then oxide. Finally, acidic workup, it will be making it tertiary alcohol. So here, alcohol, and we have two methyl groups right there, and then methyl group, and become tertiary alcohol. Please note that when we treat this ester with Grignard reagent, it is reacting twice. Two equivalents are reacting, and it is making it all the way to tertiary alcohol. Identification of the reagents. Let's get started from the starting material. Let's write the side note about, we have phenyl ring right there, 6-member phenyl, and we have an alcohol, and the alpha carbon has one alkyl group, so this is primary alcohol. Now let's compare with the product side. Here, the alcohol becoming ester. We have an ester right there, and not much of difference. Okay, so then let's go retrosynthetic analysis. And ester can be formed in many different ways, but one of them is Fischer esterification. So here, let's think about Fischer esterification. So we can make this one into a carboxylic acid plus alcohol, methanol. In acidic condition, it will be making a product ester. So then from here to here, from primary alcohol to all the way to carboxylic acid, we need to use Jones reagent. Jones reagent, you can use sodium dichromate and sulfuric acid. And in acidic condition, it will be making all the way. Water is important, aqueous acid, it will be making all the way to carboxylic acid. And then this one in acidic environment, we need acidic environment, and catalyst is required to make Fischer esterification. to make the final product? Or can we make this ester? And another method is also starting from this benzoic acid. We can treat this one with thionyl chloride. Okay. Thionyl chloride. Okay. And we can make this one into acid chloride. And this is reacting with alcohol, CH3, OH, maybe triethyl amine as a base scavenger taking proton away, then it is forming the product also. And this one, this triethylamine is forming protonated, taking proton away. Okay, this is also one of the method making the ester. Now let's go into the B. We have lactone, 6-member ring structure, cyclic lactone, cyclic ester, and ring is now dissociated. So ring has here dissociated. Ring opening process, but the number of carbon doesn't change. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the methyl group right there. Carbon skeleton doesn't change. Only ring opening process, ester into carboxylic acid and an alcohol. So then this process, the reverse process, is a Fischer esterification. Fischer esterification. The fourth process is either hydrolysis, either acidic hydrolysis or basic hydrolysis. So you can make this one into first method 1. We can make acidic hydrolysis. So you are making into strongly basic acidic condition, meaning either you can use like parasulfonic toluene, paratoluene sulfonic acid, or sulfuric acid, or sometimes hydrochloric acid, making acidic condition, or second method in aqueous solution water together. And second method is basic hydrolysis. So we are using sodium hydroxide in biphasic reaction and by acidic workup. Then it'll be have ring opening process. You can use either of these two. Now C, we have here we have nitrile and nitrile into an acid chloride or acid chloride. This one cannot be achieved in one step. We can now achieve nitrile into acid chloride in one step. We need to first make it into a carboxylic acid. Carboxylic acid first, and then carboxylic acid into and acid chloride. The first step, we need to use strongly acidic condition, and heat it up. We need to heat it up, and it'll be converting an acid chloride into, I mean, the nitrile into the carboxylic acid, and then let's use thionyl chloride. It'll be converting carboxylic acid into acid chloride and to aldehyde. So when you use lithium aluminum hydride, let me see here. Here in this case, when you use lithium aluminum hydride in excess amount and acidic workup, it is making all the way to primary alcohol twice. It will be reacting twice. So we want to stop. This one will go through first aldehyde, but it will not stop. It is because it is more reactive toward aldehyde. Lithium aluminum hydride is more reactive toward, I mean, it is also reactive toward aldehyde. It will go all the way to primary alcohol. So then how can it stop at aldehyde? Then we need to use a reducing agent. Reducing agent with reduced power. So then what would be? What would be a reducing agent from acid chloride? Then lithium trialkoxy hydride. Okay. So lithium trialkoxy aluminum hydride. Many times your trialkoxy one is butoxy, tertiary butoxy one is used for this one. Anyway, here alkoxy group is used. Then it will stop at aldehyde. Okay. It will not move further. And low temperature too. Low temperature is important too. It will stop at aldehyde. Please remember this reagent. Many times we are using lithium, aluminum, and tributoxy aluminum hydride. I mean, tertiary butoxy. Okay. Please remember this chemical reaction. We are using many different reagents. See the difference between lithium aluminum hydride versus lithium aluminum trialkoxy hydride. And D, we have amine here. So here we have amide. And there, this one into a carboxylic acid. So this is hydrolysis. This part is hydrolyzed. Then this one again in acidic condition, and heat is required. Acidic condition meaning, this one also like water. Then this will be hydrolyzed. Okay, so first this proton, the carbonyl oxygen will be protonated first, and the water will be attacked, nucleophilic attack, and followed by like hydrolysis. And again, going back here, amide into carboxylic acid. Then what about carboxylic acid into amide? Remember this one. This one is acidic proton right there. When you have acidic proton, we cannot use this nitrogen nucleophile. Nitrogen nucleophile is also basic. So acid-base reaction will occur first. So what you need to do is remove this acid halide. So let's use thionyl chloride. Then let's activate it. And also get rid of the proton. It will be plus SO2 plus HCl. And this one is now, we can treat this one with, this is most reactive. Acyl chloride is most reactive carbonyl compound. We can treat this one with a nitrogen nucleophile. and it will be reacting. This one will be attack, and it will be moving up to the final product. Now let's see here. Let me erase this one. We have an ester. We are given an ester, and we are ending up with an aldehyde. So we need to hydrolysis of this one into an aldehyde. How can you do that? Let's let's think about it. So we can do ester into an aldehyde. We need to have a reducing agent. This is reduction, partial reduction. This is achieved by diisopropyl, diisobutyl aluminum hydride. We call this one sometimes dibar, or simply dibar. The structure is diisobutyl. So the aluminum right there. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Diisobutyl group, and then hydride. So this is diisobutyl. So this one is isobutyl group. Two of them isobutyl. And low temperature is important. We need to control the reaction. Low temperature, typically negative 60 degrees C or negative 72 degrees C, can be achieved experimentally in the lab and followed by acidic workup. Mildly acidic condition required because acidic condition can be reacting with the aldehyde too. Then it can be converting ester into an aldehyde. Please remember also diisobutyl aldehyde is converting an ester into an aldehyde, very specific reaction. Section 2, reaction mechanisms, acid catalyzed hydrolysis of an ester with isotope labeling. Here, this is very useful synthetically and also in our own practices. Okay, so first, let's analyze our reagent, given reagent. This one is an ester and ethyl ester. And here water is this one. This one is oxygen, 18 oxygen. Remember 18 oxygen is same. This is acting as same chemically as with 16 oxygen. The number of protons same, number of electrons same. The only difference is number of neutrons. So it is acting exactly same with the main oxygen, which is 16 oxygen, but different in mass. So later we can check it. Also 18 oxygen is unstable, relatively unstable. We can check it also, many different methods. Isotopic labeling is very useful to find the mechanism. All right. So then ester is stable. Remember, ester is stable. Ester and amide is a stable carbonyl compound. In acidic condition, this is acidic hydrolysis. Okay. Here we have sulfuric acid, and heat is required right there. So acidic hydrolysis, water is a nucleophile. This water is a nucleophile, but this is a weak nucleophile. Why? Because it's neutral. Oxygen has two lone pairs, but oxygen is strongly electrophilic. and it is strong in electronegative, so the lone pairs are tightly held by the oxygen. It is weak, so we need to first activate it. Activate the ester by protonation. That's the first reaction in acidic condition. In acidic condition, please activate it ester and then followed by nucleophilic attack by water. And it'll be moving on. Many steps will follow. Okay, so then let's first use here water. Water will be protonated, completely protonated by this strong acid. Strong acid. So then it'll be one side reaction. It'll be making protonated plus sulfur hydrogen sulfate ion. Okay, so this one is strong base, strong acid. But we have extra amount of water, so we have both water and hydronium ion present in the solution. So we'll be using water as a nucleophile and hydronium ion as source of proton. This is nucleophile, weak nucleophile, weak base, and this is strong acid. Source of proton. Okay, let's get started. Let's first protonate it. Let's write it. Hydronium ion and protonate it. Protonate it, making into activated. And this protonation is all equilibrium process. So let's protonate it, making positive charge on the oxygen. And now water can be attacking. Water can attack. This water has a lone pair attack and push up the pi bond to this oxygen. Again, this is equilibrium process. Now we have here OH and OH H positive. And let's use water as a weak base. So then let's deprotonate it. Deprotonate it, making into the intermediate, this OH and OH. So you can make this one into, we have two products right there. So here we have two hydroxyl group. And you need to make this one into leaving group. You need to make it leave. But methoxide ion is a strong base. It is not leaving as it is in acidic condition. So we need to protonate first. Let's protonate it. So this one, that's the difference between acidic hydrolysis and basic hydrolysis. We need to make this one protonate first and make it into good leaving group now, positive charge. So this is good leaving group now, and then OH and OH. So this, now we can move either of these two. We can make this one coming down and it is leaving, and then deprotonation. Here deprotonation, then it will be making this product. Or we can make this lone pair coming down and it's leaving, then it will be two-step deprotonation. It will be making this product. Okay, so it's either way, because both of them OH, the lone pair of both of them can be coming down, make them leaving group leaving. So it is because here we are differentiating between oxygen. One is 16 oxygen, the other one is 18 oxygen. So we have two different products mixture. Now let's go into multi-step synthesis. Here we have a 17 carbon backbone. This one is backbone of a steroid. This 17 carbon backbone for 3 6-member ring fused and 5 member ring here. And we have two functional groups. Here we have ketone right there, and here we have alcohol, and the alpha carbon here has two alkyl groups, so this is secondary alcohol. And here secondary alcohol is preserved, but the ketone is turned into a alcohol. So this is reduction. Let me see. The carbon is lost, so we need to cleave this bond, make into leaving. How can you achieve this one? How can we get rid of the carbonyl group? We can think about Wittig reaction. I mean, not Wittig reaction, ozonolysis. So any reduction of carbon skeleton, carbon skeleton, we can think about ozonolysis. Double bond, here double bond, carbon, alkyl group, and we take it, and there is making. This is leaving, CH2, and cleavage of double bond, or hydrolysis. Hydrolysis of an ester, or amide. Make it cleavage and make the carbon group leaving. So there are these methods we can think of here, but it is not double bonding, carbon double bond. Then let's think about hydrolysis of an ester. But here currently it is a ketone. How can it convert a ketone into an ester? Okay, so then let's think about the Baeyer-Villiger reaction. Baeyer-Villiger reaction. Let's choose MCPBA, metachloroperoxybenzoic acid. So, and meta position we have chlorine, and here OOH. This is metachloroperoxybenzoic acid. When you use this one, then it will be inserted in between the carbonyl carbon and the following alpha carbon, and the migration aptitude here, migration aptitude in this Baeyer-Villiger reaction, tertiary alkyl group is best. Secondary alkyl group and phenyl ring is similar. Primary alkyl group and then methyl in this order. So then here we have methyl group. We have secondary alkyl group right there. So then secondary alkyl group has priority right there. Secondary alkyl group has priority then compared to primary alkyl. So when you use Baeyer-Villiger reaction, this oxygen, this oxygen will be inserted between the carbonyl carbon and alpha carbon. So it will be making 5-member ring structure. And here alkyl group. The ring, let me represent two alkyl groups. And then it will be inserted right there. Oxygen is inserted right there. This oxygen is inserted. and then carbonyl and methyl group right there. Here let's use hydrolysis. And because we have hydroxyl group right there, secondary here, this hydroxyl, we cannot use acidic condition. Acidic hydrolysis will be making the secondary alcohol into an alkene. So then let's use basic hydrolysis. Basic hydrolysis. So first sodium hydroxide in biphasic reaction followed by acidic workup. Then it will be making this one into alkyl group, and it'll be cleaved. It'll be making OH here. Then it'll be making into final product. Okay. All right. So now let's think about it. How to analyze this one? We have the carbon skeleton doesn't change. The 17 carbon backbone, the steroid backbone doesn't change, but the functional group, we have two functional group. One is secondary alcohol. The other one is ketone. The secondary alcohol was preserved, but the ketone was transformed into a secondary. I mean, the ketone is transformed into secondary alcohol. Then, as you thought about the reduction of decreasing cleavage of carbon skeleton can be achieved either by ozonolysis or hydrolysis. And here we chose hydrolysis. But ketone is not prone to hydrolysis. Ester is prone to hydrolysis. So let's convert ketone into an ester by using the peroxybenzoic acid, the alkyl peroxide. And then using the migration aptitude, we see that the oxygen is inserted in between the carbonyl carbon and next secondary carbon. And they're using basic hydrolysis. Why? Because we have a secondary alcohol. Secondary alcohol is preserved. So in order to preserve this one, then we have to use basic hydrolysis, sodium hydroxide, followed by acidic workup. Okay. Now going to synthesis challenge, propose an efficient multi-step synthesis. Here we have benzene ring, and in para position we have methyl group, and we have a long carbon chain right there. In para position, let me see. Para position to each other, and we have carboxylic acid. Here we have carboxylic acid at the end. So carboxylic acid. And now let's see the product. Product, we have new carbon-carbon bond right there. This is the new carbon-carbon bond, carbon-carbon double bond. And think about Wittig reaction. When you see the double bond, we see the Wittig reaction is forming the double bond. And so let's go retrosynthetic analysis. Wittig reaction is between either ketone or aldehyde and the Wittig reagent, triphenyl phosphide, triphenyl phosphorus ylide. So let's think about, so this part is as it is, and then 1, 2, let me draw it again. So this part is 1, 2, 3, 4. This should be becoming an aldehyde because we have a hydrogen there, aldehyde, and here methyl group as it is, and plus triphenyl. So triphenyl and ylide. So that this one is carbanion, but we have two methyl group right there. So here methyl, and they will be making this product by the Wittig reaction. And now how can it convert carboxylic acid into an aldehyde? So there are a couple of different methods. First, make them into an acid chloride by using thionyl chloride, and acyl chloride is lithium aluminum trialkoxy hydride. Will be make them into an aldehyde, right? Or let's make them let's make it into an ester. So let's make it into, let's say, CH3. Let's choose acetic acid, CH3COH. I mean, oh, this one is alcohol. Okay, then methanol. Let me use methanol. Let me use methanol, CH3OH, and in acidic condition, then it'll be making into, this is Fischer esterification, Fischer esterification. It'll be making into an ester and followed by taiba. So at low temperature, then the ester is turning into an aldehyde. We can use either method. Either way, it'll be making an aldehyde, and aldehyde is turning into a double bond by using Wittig reaction. Okay, let's see. Synthesis challenge. Propose an efficient and logical synthetic route to convert A to B. Here we have two functional groups. We have ketone right there, ketone, and nitrile. Here nitrile, and two six-member ring, they are fused, and nitrile turned into a methyl group, and ketone is preserved, conserved. Ketone is conserved, preserved. Okay, so ketone is not changing, but methyl nitrile is converted to methyl group. So we need to protect the ketone by acetal formation, protection and deprotection. Okay, so all right. So then the first step, let's treat this one with ethylene glycol in acidic condition, and let's take water out. Water is byproduct. Then the ketone is turned into, everything else will not change. Nitrile is now reactive. This is turned into an acetal. Acetal right there. And now we can do chemical reactions. Acetal, excuse me, acetal is going back to the the ketone in acidic condition, but this one is inert. Acetal is inert in basic condition. So then let's do acidic, basic condition. Think about basic condition. So here, basic hydrolysis. Basic hydrolysis. So first, sodium hydroxide in biphasic reaction, water and organic solvent, and heat it up because nitrile is very inert, very stable. Nitrile is stable compound, followed by diluted uh, acidic worker. So acetal is not is intact, is not is conserved. Then this is turning this into, acetal is preserved. I mean, here acetal is preserved, and then this is turning into a carboxylic acid. And oh, not carboxylic acid. nitrile. Okay, correct. Carboxylic acid. Let me see. Let me see. This one, C, CN, C, N is reactive with this condition, then reacting, it will be leaving, and in strongly condition, basic condition, okay, it is true. And now let's make it into, let's make it into, let's treat this one with thionyl chloride and convert this carboxylic acid into acid chloride. Then acid chloride will be reacting with lithium aluminum trialkoxy hydride. It'll be turned into a aldehyde. Aldehyde. And then finally, strongly acidic condition. Strongly acidic, strong like acidic condition. Then it'll be acetal will be deprotected, forming back to ketone. Or from here, let me copy from this acetal, copy this one into here. Then acetal we can use thiol here, isobutyl aluminum hydride in the low temperature. Then not only this one turning the ester into an aldehyde, this is also turning this nitrile into an aldehyde. So this will be converting this one into aldehyde directly. And from aldehyde, we need to, final step is acidic workup. Then acidic, let me see. Okay. Here, let's choose like Wolff-Kishner reduction. So potassium hydroxide and hydrazine and heating up in basic condition. Then it'll be turning this aldehyde into reduction into methyl group. And this is the acetal will be preserved in the basic condition. Finally, acidic workup. Finally acidic workup. And then, so this method, so I need to add, I just found out here, I have to add one more step. I need to have Wolff-Kishner reduction too, because I need to take this the aldehyde off. So Wolff-Kishner reduction, I can take this aldehyde off. All right. Okay. So number 6 was really bit challenging because we are preserving the ketone, but transforming a nitrile into a methyl group. So it was a kind of a long process. Okay, so here in worksheets 4D, 5D, and 5E, we practiced putting them together, the knowledge and pieces we have studied, and then make them into a product. So I highly recommend you to print it out a blank paper and then repeat this one twice to get familiar with the reagents and the products and the mechanism. Thank you, everyone. Let me see you in the lecture.